So hello everyone to the last session of today. This is the third PQC session, this time on hardware. And so we have three talks. The first two are in person and the final one will be an online talk. And the first presentation, the first talk will be about gadget-based masking of streamlined and true prime decapsulation in hardware. And it will be given by Adrian Marotzke.
Thank you very much. So, I'll be presenting our gadget-based masked implementation of streamlined and true prime. And the slide? No. There we go. So the area we are, of course, side channel protected implementations of post-quantum crypto, specifically lattice crypto, where, of course, we use side channel information to try and extract the key. And one thing which has been shown in many different papers over the past few years is that there are a lot of attacks against side channel protected implementations, even like high order mask implementations, such as, for example, a fifth order mask Kyber. They're still being broken. And another result from the research was that the FO transform, a core component of a lot of these lattice algorithm, also forces us to use even more masks. And so when we look at these lattice algorithms, they have lots of different components. You have polynomial arithmetic, you have hashing, you have modular reductions, error sampling, and lots of different stuff. And so when you see these mask implementations of these algorithms, there's usually a mix of Boolean and arithmetic masking on an algorithmic level, depending on what is more efficient. So here, for example, you can see a mask decapsulation of Saber, and it starts off in the arithmetic domain, then you go to Boolean, do some operations, then go back to arithmetic, then more operations, then back to Boolean again. So lots of masking conversions. And these masking conversions are not always so nice, because on the one hand, they're expensive to do in the first place, but also they're a common attack target. So several of these attacks against mask implementation specifically attacked the masking conversion between Boolean and arithmetic masking, or vice versa. So our approach is basically, let's do away with all of this mask conversion, and instead of masking on the algorithmic level, use gadget-based masking. And so what this means is that we basically replace each gate with a side channel secure composable gadget. Just for example, an AND gadget. In this case, an example is the Pqc Ii gadget. And of course, we can combine these two gadgets in arbitrary ways because they are composable. And gadget-based masking has been very successfully used for symmetric crypto, like AES or Present and so on. But they've never been used for public key crypto, because public key crypto, you have like number theoretic structures, polynomial arithmetic, or modular exponentiation, and it was just not considered feasible to apply gadget-based masking to this. We show that this actually is possible by applying it to the streamlined and true prime decapsulation, and specifically using the Pqc Ii mask gadget. So so a short primer on streamlined and true prime. It's a structured lattice-based chem. It was one of the alternate finalists. Unfortunately, didn't get selected. The main operations here is the polynomial multiplication in two different rings, RQ, R3. They're almost identical except for the coefficient modulus. We also have some hashing, specifically SHA-512. We have a weight check, where you basically check how many non-zero elements there are in a polynomial, and if it's a specific amount, otherwise it gets replaced, as well as some rounding and reduction mod 3. On the right, you can see the actual algorithm. The stuff we're actually masking is the thing in blue, because that's actually the operations that deal with the masked, that deal with the secret key. And specifically, we are implementing the recommended parameter set S-entropy 761. So the main challenge is the polynomial multiplication in the RQ, which is like the big polynomial ring. And the thing is that a quirk of the streamlined true prime is that it has what's been called a big X small polynomial multiplication. And what that actually means is that we have one public polynomial, either the public key or the ciphertext, that it actually has 13-bit coefficients. And the second one, which is the secret polynomial, part of the secret key, this actually only has coefficients that are either -1, 0, or 1, and nothing else. And this is actually what will allow us to actually apply gadget-based masking in the first place. as we'll see on the next slides. In general, of course, we want to minimize the number of nonlinear gates, specifically and or, because these are the ones that are actually expensive when applying the HPC2 gadget. Things such as XOR, for example, or NOTs are almost for free in comparison. And of course, we want to balance the latency and area in order to get like a somewhat balanced implementation. Because of course, having a high latency for like a specific operation also means we need more registers for pipelining, which then also increases the area again. So if we look at the polynomial multiplication, basically what we've implemented is a schoolbook multiplier that doesn't actually contain a multiplier. Instead, using purely a mask adder and a multiplexer. So what we basically do is we take this big public polynomial, we put this in a RAM, and then we take one coefficient at a time. We apply its additive inverse, so q minus a, and then use a multiplexer using the coefficient from the secret polynomial as the select signal to basically select between then either a, minus a, and 0. And then we use an adder to accumulate this in an accumulator RAM. Of course, we also need to then apply a modular reduction, so we actually stay in the mod Q. And for this, we can use a conditional subtraction. So we again have then a masked adder, which we reroute to do a subtraction, and then we use the overflow, sorry, not the overflow, the carry out signal to then, as an input for a second multiplexer, to basically decide whether or not this subtraction was actually needed in the first place, and whether or not we use the original value or the value subtracted Q, so that we stay in the range of 0 to Q minus 1. And of course, the multiplexers, they of course have to be masked. So the three-way multiplex of public values with the secret select signal, and then also the two-way multiplexer of secret values and a secret select signal. And of course, once we go through the entire public, once we've gone through the entire public RQ polynomial, we then basically rotate this once according to the LFSR, which corresponds to the polynomial of RQ, so x to the power of p minus x minus 1, and then repeat the entire process for every single coefficient in the secret polynomial, rotate again, and so on until we've rotated entirely, once we've rotated the entire polynomial once, and then we have the completed polynomial multiplication, the result in the accumulator RAM, and we're done. For the polynomial multiplication, R3 is much simpler. Of course, the structure is the same. We again have this sort of schoolbook multiplier with the rotate one polynomial and adding it together. But because, of course, now all values for both polynomials are only minus 1, 0, and 1, we don't have really any multiplier at all. We can just directly write the Boolean expression of our multiplier and our accumulator and our modulo. You can see the Boolean expression right here. And this basically does the entire coefficient multiplication and accumulation. For the weight check, then also we can again reuse that adder, that Sklansky adder. Oh yeah, I forgot to mention, we're using a Sklansky adder, a parallel prefix adder, because this was found to have the best balance between area, latency, and randomness requirements, which is why we're using it. So for the weight check, we simply use Sklansky adder to sum up all the absolute values of a polynomial, XOR this with a target weight, and then again input this into a two-way masked multiplexer to decide whether or not we want the original value or this overwritten value. For the module 3, we have to do a bit of rewiring again, because when we want to take coefficients that are in ZQ and then map them to RQ, we basically have to somehow compute mod 3. And what we here use is the application of the rule that 2 is equal to minus 1 mod 3. And basically, we repeatedly apply this. And this is what the structure which you see on the right. In this case, we're not using a Sklansky adder. We're using the simpler Ripple carry adders because the adders are only like 1 to 3-bit adders. So doing some sort of parallel prefix adder does not make sense here. And the thing, of course, is that this can also be applied for the rounding operation. Basically, what you do is you first apply this mod 3 to the polynomial and then add that back to the original one, and that's how you get your rounded polynomial. And finally, the SHA-112. So the biggest operation here is the 64-bit addition. For this, we use a 64-bit mask Sklansky adder, which of course is pretty big. The linear operations, specifically like the sigma functions, these are fairly easy with using HPC gadget. It's just XOR and rotation, so basically free in comparison. The nonlinear functions, they have to be rewritten a bit, or we rewrite them a bit in order to reduce the number of AND operations, because this is ultimately then more efficient. A bit of a funny side note is that, as far as we can tell, no one's ever actually published anything about masked SHA-512. I mean, it's available in stuff like smart cards for a while now, but no one's ever actually published anything on the results. So we think that this is actually the first one. And on top of that, it's even arbitrary order. So in case, for example, you're like wanting to do, let's say, a masked Sphinx Plus with the SHA-2 variants, this might be of interest to you as well. So what results do we get if we apply all of this gadget-based masking? So it's 1.87 million cycles, which admittedly is quite a lot. But we have two special things. One, this is independent of the masking order. So we can increase the masking order to 1, 4, or however high we want. It stays 1.87 million cycles. And changing the masking order is super simple. It's a single VHDL parameter, and then all you have to do is resynthesize it, and you're done. The second thing is that, yeah, the SHA-512 is by far the largest component we have. It's depending on the exact masking order, it's between like 58 to 61% of all lookup tables and flip-flops. So it is massive in comparison. All the rest is very small. We look at the concrete numbers, and then, for example, first order, we're at like 20,000, just shy of 20,000 lookup tables, 20,000 flip-flops, 8.5 block RAM, and 4 DSPs. And running at 200 megahertz. If we compare this to two other masked hardware implementations, one of Sabre, one of Kyber, the lookup tables and flip-flops is more or less the same for Sabre. We do use more VRAM, but we use almost no DSPs in comparison because we don't have an actual multiplier. Though, of course, our clock cycles is way, way higher, almost 2 order of magnitudes higher. Comparison to the Kyber implementation, however, even our fourth order implementation actually has has a lower area. Though again, our clock cycles is a lot higher. Finally, we also synthesized it for ASICs using the NAND Open Cell library. There, for the first order, for example, we have about 201,000 gate equivalents, as well as 189 kilobits of SRAM, again running at about 207 megahertz. For the side channel evaluation, one additional benefit of the HPC gadget is that we can do formal verification on it. Specifically, we're using the Verica formal verification tool, and we're in the glitch extended probing model. So that basically can formal verify that our individual components are actually secure and that they don't leak. All of our components pass first and second order verification. Some components, specifically the mod 3 and the multiplication in R3, they don't pass third order verification because they just didn't complete. We ran them for quite a while, but at some point we had to cancel them because they just wouldn't terminate. That being said, in addition to formal verification, we also applied practical verification, practical evaluation, sorry, with 10 million traces and just t-test. All tests showed no leakages, went also with our first order mask implementation and a first order t-test. None of our modules showed leakages. If we applied a second order t-test on the first order modules, we again saw some leakages, which also verifies our setup was actually correct in the first place. So yeah, as a conclusion, we showed that we showed a arbitrary order mask post-quantum hardware implementation using gadget-based masking is actually feasible, and as part of that, actually created a high order or arbitrary order mask implementation. Something which is simply not considered feasible before. Our cycle count, while admittedly relatively high, is independent of the masking order. Though, of course, as the orders go up, we do see that the frequency can decrease simply due to the increased routing complexity. That is something to keep an eye out. And finally, thanks to the use of the secure gadgets, we can formally verify our implementation, but also as a backup, we also did practical side channel evaluation. A few things maybe for the future. So for one, of course, we applied this to streamlined entry prime. The question would be, of course, can this be applied to Kyber? Because, of course, Kyber is the standard now. And the answer is basically yes. Kyber actually also has the big X small structure, except the small polynomials in Kyber are a bit bigger. They're not -1 to 1. They're, depending on the parameter set, -2 to 2 or -3 to 3. So your multiplexer gets a bit more complicated. But otherwise, you can actually apply it very similarly. The bit of a downside, of course, is that Kyber managed the use of NTT, so you basically have to remove that first. But you don't actually need a masked entity in that case, so you can actually still apply it. You just have to basically remove all the NTT structures first. The second thing is that basically removing the SHA-512. It is by far the largest area consumption in our implementation. So exchanging it for a catch-up implementation, for example, would basically reduce the area most likely by half, more or less. Of course, replacing it would mean that you're no longer compatible to the streamlined entry prime spec. But for example, if you're applying it to Kyber, which uses catch-up, then this will make the approach far more efficient. Another thing is that our BRAM is a bit high. The BRAM usage of these 189 kilobits, most likely this could be optimized a bit by actually just being a bit more careful about how many RAMs we instantiate. We were a bit careless there. And finally is whether or not this can be applied to the encapsulation of streamlined entry prime, in addition to the decapsulation. Almost all of our modules can be reused for that. The only one module you would actually need is the sorting module that streamlined entry prime uses to generate the short polynomials during the encapsulation. This is the one module you would have to additionally implement. Other than that, all of the modules can be reused. And the final and the question might here also be then, can this approach be applied to the key generation? And the answer is almost certainly no, unfortunately, because key generation of entry prime of streamlined entry prime requires a polynomial inversion, and this probably is not possible with the gadget-based approach. And final thing is that the Verilog and VHDL source code implementation is available in the artifact. So if you want to try it out, have a look, then please look at the artifact. With that, thank you very much. Any questions?
Thank you for the nice presentation. Are there any questions from the audience? There appears to be a question.
All right, thanks for the presentation. Why is the polynomial inversion not really amenable to gadget-based masking?
Because at one point you need a multiplication, like during the if you use the algorithm, for example, like the extended GCD algorithm, you basically have to take 4 coefficients and do a fuse multiply add. And at that point, you need a multiplier. There's no way to do this with this sort of trick of using this like big X small structure. You have just two 13-bit coefficients you have to multiply together. And I mean, you could still do gadget-based masking and basically have like 13 of these 13-bit Sklansky adders, one after the other, but the latency would be incredibly high, and also the area overhead would be incredibly high. So I mean, it's technically possible, but the area overhead and the latency overhead would be massive. So it's really not feasible.
Yeah, thank you.
Yep, thanks.
Any other questions from the audience? If not, then I have a question. So what would it take to convert this design to a more like what we've seen previously with B2A, A to B conversion, because they are mostly also based on masked adders?
How exactly do you mean the question? Like, you mean like having a traditional implementation of like streamlined entry prime?
Yeah.
So of course, what you would need is that, I mean, you would need for the polynomial implication, you would then of course do that in arithmetic masking. And so you basically have, okay, you start off in the arithmetic domain, you do one polynomial, the polynomial implication RQ. You would then have to probably modify this then to Boolean to do the mod 3, then go back to arithmetic for the multiplication R3. For the weight check, that could be done in arithmetic masking, but for replacing the polynomial, you'd have to go back to Boolean. So you'd probably have to go back and forth like 6 or 7 times.
Oh, so you mean by because you save all these intermediate conversions that you save a lot of time.
Yeah, because of course we have to do no masking conversion at all. It's because it's 100% Boolean masking, so we don't have any of the overhead of going back, going like arithmetic to Boolean or back and forth. And of course we don't have that potential attack vector of attacking the mask conversion, because it's just not here. We don't convert anything.
There are no questions, no further questions from the audience. Then let's thank the speaker again.
Okay. Thank you.
And our next talk is about an efficient ASIC architecture for low latency classic McAleese decoding. And the talk will be given by Daniel Farnig.
Thank you for the introduction. Hello, everyone. First of all, thank you for attending the presentation. I want to talk about our low latency ASIC implementation for the decoding routine of classic McAleese, as well as the hardware optimizations we introduced to increase the area efficiency of our design. So, classic McAleese is a key encapsulation mechanism whose performance characteristics were demonstrated for several FPGA implementations. However, there's no ASIC implementation. And because the efficient design points might differ between FPGA and ASIC implementations, we wanted to implement an optimized ASIC design for the decoding routine for classic McAleese. Our design goals were to achieve a low decoding latency with high area efficiency. And we also wanted to support constant time operations as well as a long-term secure parameter set. For a little bit of background on classic McAleese. Classic McAleese is a key encapsulation mechanism that is a 4th round candidate in the NIST Pqc standardization process. It is a code-based CAM and utilizes binary Gopper codes and is based on the asymmetric McAleese crypto system, or rather a dual variant of this system proposed by Niederreiter. The underlying crypto system allows, among others, for the selection of parameters, binary field size M, code length N, and number of errors T. And for our design, we selected a parameter set with the parameters M13. So we operate on a 13-bit Galois field. We have a 6,960 code length and 119 errors, which correspond to a 266-bit security level. With these parameters, we can then derive a key. The private key consists of a Gopper generator polynomial G and a random permutation of so-called support elements, which are then N field elements of the underlying Galois field. With these 2 components, the generator polynomial G and the support vector, we can derive the public key, which is a so-called parity check matrix H, which is then brought to systematic form, so we only have to store the non-systematic part. Shown here is the principle of the underlying crypto system. Classic McAleese comprises these 2 routines, encode and decode, which correspond to Niederreiter encryption and decryption. And the encoding step basically takes a plaintext, an error vector E of n bits with T errors, in our case 119 errors, and multiplies it by the public key, the parity check matrix H, to yield a syndrome S, which is used as a ciphertext. And the decoding routine on which we focus on the following then reconstructs the plaintext E from the syndrome S by first computing an error locator polynomial lambda using the Gopper generator polynomial G. And because the roots of this error locator polynomial correspond to the error positions, by evaluating this error locator polynomial for all support vector elements, we can then reconstruct the error vector E. Shown here is the high-level architecture of our decoding module. And in addition to the two steps I mentioned, the computation of error locator polynomial and the polynomial evaluation, we also implement an additional step, the computation of a double-sized syndrome, which is required to correct T errors with the decoding algorithm that wasn't specifically designed for Gopper codes. When we look at the block diagram of our decoding module, at the bottom we see a combined evaluation module, which implements the first and the third step of the decoding operation, and the second step, the computation of error locator polynomials, is implemented in a dedicated module. And because of this combination, I will start to describe the error locator polynomial computation first, and then continue with the first and third step. For the computation of error locator polynomials, we utilize an inversionless variant of the commonly employed Berlekamp-Massey algorithm, which is an iterative algorithm that in each iteration first computes a discrepancy delta, shown here on line 4 of the pseudocode, and then uses this discrepancy to iteratively update the coefficients of the error locator polynomial. The inversionless variant that we use is basically a trade-off between a costly field inversion with multiple field multiplications, but the resulting polynomial possesses the same roots as the polynomial computed by the normal Berlekamp-Massey algorithm, so that we still get the same result for decoding. Looking at our implementation, we implemented a module which implements the two subsets of each iteration, the discrepancy computation and the coefficient update, in two dedicated submodules. And it is a folded design, so we don't operate on all coefficients of the error locator polynomial in parallel, but rather we use a folding factor of 6, which means that we operate on blocks of coefficients of 20 coefficients in parallel. Looking at these submodules in greater detail, our discrepancy computation module utilizes this shift register structure shown at the top with multiplexes, which allows us to reduce the switching activity and only shift our syndrome elements every 8th cycle. And this is followed by a multiply and add tree structure with a shift with a register stage in between to keep the critical path short. For the coefficient update, we implement this step in a systolic array consisting of 20 processing elements. And each processing element can compute the coefficient update of one coefficient and then stores coefficients and temporary values of this algorithm in registers, which are then fed into multiplexers, which allows us to implement some additional optimizations. The first optimization we implement for Berlekamp-Massey error locator polynomial computation is the interleaving of the iterations of this algorithm. So after we updated one block of error locator polynomial coefficients in one iteration, we can then directly use these coefficients to begin discrepancy computation of the next iteration. For the folding factor of 6 that we used, this then leads to a latency reduction of 38%. And we also implemented an additional optimization, which results from the observation that in the first iterations of the Berlekamp-Massey algorithm, the upper coefficients of the error locator polynomial are 0. And because we operate on blocks of the error locator polynomial, we can then simply skip the update of all 0 coefficient blocks, which gives another 15% latency reduction. Shown at the bottom of the slide is a comparison of our Berlekamp-Massey implementation with the Berlekamp-Massey implementation from the FPGA design from Wang, Sefa, and Niederhagen, which is the FPGA design referenced on the classic McAleese website. And in the following, I will refer to this design as the baseline design. When we compare the two implementations, we can see that our design requires significantly fewer arithmetic modules than the baseline Berlekamp-Massey implementation, as well as fewer registers, but at the same time allows to significantly reduce the latency required for computing error locator polynomials by the optimizations I just described. Looking at the next steps in classic McAleese decoding, polynomial evaluation. For polynomial evaluation, we use the rather naive approach of Horner's method, which possesses a regular structure and therefore allows us to iteratively compute polynomial values in a systolic array. The systolic array we designed for this consists of 120 processing elements where each processing element updates the polynomial value by multiplying partial values with support vector elements and then streaming these support vector elements through the array. The last step I want to describe is the computation of this double-sized syndrome. A double-sized syndrome is computed by computing a matrix vector product of double-sized parity check matrix H2, shown at the top right of the slide, with the syndrome. And when we look at the double-sized parity check matrix, we can actually see that it can be iteratively computed row-wise by starting with the first row, which consists of the squared inverses of Gopper generator polynomial values. And then we can iteratively compute rows of this parity check matrix by multiplying a previous row with a vector of support elements. And we map this iterative structure also on a systolic array, where we compute columns of the double-sized parity check matrix by streaming column values through the array and then accumulating the values of the double-sized syndrome locally in a processing element. So now for the first and the third step, the polynomial evaluation and double-sized syndrome computation, we actually combine these two steps into one systolic array. Because these approaches are very similar, we don't have to instantiate two distinct arrays with 120 processing elements each, but instead we only instantiate a single array that can then execute both steps. Shown at the left of the slide is then a comparison of our implementation for polynomial evaluation and double-sized syndrome computation with the baseline design, which again is the FPGA design from Wang et al. Looking at the top at table 4 is a comparison of polynomial evaluation approaches. And while our design uses Horner's method, the baseline design uses an additive FFT, which possesses a significantly reduced multiplicative complexity. So we can see that the FFT approach requires significantly fewer multipliers than our design, and at the same time also about 7 times fewer cycles. So only from a polynomial evaluation standpoint, this approach seems to be advantageous here, but our design reduces the required register count and SRAM macro size and requires no additional operation for polynomial evaluation. Because when using this additive FFT approach, this evaluates a polynomial in a specific order. And we later need polynomial values in the order corresponding to the permutation of the support vector, which then causes this additive FFT implementation to require an additional memory readout operation, which eliminates the latency advantage of this much faster polynomial evaluation. looking at the bottom, table 5, there's a comparison of double-sized syndrome computation approaches. Also here, our design requires more multipliers than the baseline designs, but rather focuses on a reduced register and SRAM macro utilization to achieve comparable performance. But now that we take our optimization into account, that we actually combine these two systolic arrays into one array, we only have to instantiate this array once. So in total, we only require the resources shown in the bottom table, so only 130 multipliers in total, while the baseline design implements these two steps in distinct modules. And when we sum the arithmetic resources of both steps, we then also get a comparable multiplier count for this implementation. The modules I described were implemented in Verilog and System Verilog, and together with additional on-chip test logic, we integrated our decoding module into a test chip, which was taped out and manufactured in a 22 nanometer technology node. And because the design or the clock frequency of the design was not limited by the logic of the decoding module, but rather by the employed SRAM macros, we implemented an additional optimization where we introduced a multi-cycle path across these SRAM macros to effectively operate them at half the frequency with double the width, which then allows us to operate our test chip at a clock frequency of 2 gigahertz. Shown here is a summary of results of our test chip, as well as our decoding design labeled here IBM, with a clock frequency of 1 gigahertz for comparison purposes, as well as a baseline design at 1 gigahertz. The baseline design here, again, is the FPGA design from Wang et al. And because the authors mentioned that it's possible to reuse their open source Verilog code to create an ASIC design, we did just that. We took this design and the performance optimized design point and only exchanged the used block RAM macros for appropriate SRAM macros from the 22 nanometer memory library. When comparing both designs at 1 gigahertz, we can see that our design requires significantly fewer cycles for decoding operation, but at the same time only occupies a smaller area footprint and requires lower power dissipation than the baseline design. And let's look at these results in greater detail. Shown here is a breakdown of the results. Shown on the left is a comparison of the latency of both decoding implementations. When we look at the baseline design, we can see that the additive FFT polynomial evaluation requires significantly fewer cycles than our implementation, shown in blue and green. However, our implementation can compute error locator polynomials and the double-sized syndrome significantly faster, and doesn't require this additional memory readout operation at the end of a decoding operation, which then gives it an latency advantage. Looking at the area and power requirements of both designs, we can see that the baseline design was initially an FPGA design and therefore not optimized for reduced block RAM or SRAM usage. But when applying this design to an ASIC implementation, in contrast to an FPGA implementation, SRAM is not, so to say, for free. We actually have to spend area to implement this SRAM.
Hello, everyone. Thank you for attending my talk, which is titled...
Okay, sorry.
I don't know what just happened.
I'm very sorry. Okay.
I think somehow another presentation just started or something. Yeah.
I just continue, right?
Yeah, just keep going.
Okay, so for an FPGA implementation, blockgram is already on a chip, that's fine. For an ASIC implementation, we actually have to spend area for blockgram. So here we can see that for an ASIC implementation, it is advantageous to really reduce the SRAM requirement of an implementation. Also looking at results of our manufactured test chip, shown on the left is measurement across supply voltage of the maximum clock frequency for which we could verify a correct decoding result. We can see that our test chip indeed can achieve the 2 GHz clock frequency, although at an increased supply voltage compared to simulation results, which we identified to be caused by an IR drop at the beginning of a decoding operation, which was caused by the on-chip clock generator. Due to this IR drop, the required power dissipation of our implementation is also slightly increased compared to simulation results, although still significantly lower than the power dissipation of the baseline design. To summarize, we presented the first optimized ASIC implementation for the decoding step of classic McAleese, which is an area-efficient constant time design. We also taped out and manufactured this design in form of a 2 GHz test chip, which allows to execute the classic McAleese decoding operation with a low latency of 6.64 microseconds on a very small area footprint. And through the additional hardware optimizations that we introduced, we were then able to achieve an almost 2x speed up for computing error locator polynomials, while at the same time requiring fewer arithmetic resources. And by combining the other 2 steps of the decoding algorithm, we can then also increase the area efficiency of our design. That concludes my presentation. Thank you for your attention, and if you have any questions, I would be happy to answer them.
So there's already the first question from the audience. Don't have to ask.
Thank you for your talk. Very nice results. It's very nice to have a tape out, actually. It's really great. Just one question. Why do you do the PKE and not the chem? There's not much missing to do, actually, testing McAleese decapsulation, but you just do decoding. Why do you have some steps missing, and what will the cost to have full decapsulation implemented?
So we focus on the PKE instead of the complete decapsulation. First of all, because of time constraints, and also because the remaining steps, the hash function and the plaintext confirmation routine are, I would say, already relatively well studied, right? So, yeah.
But I mean, but it's really interesting to see how this would affect the overall ASIC area and overall cost.
That's correct. That would be interesting, but we choose to focus only on the PKE portion of the chem.
Thanks.
Any other questions from the audience? I do have a couple of questions. Do you happen to know a number in gate equivalents? Because that's the thing I always know.
Not from the top of my head, sorry.
Okay. Then maybe can you go back to the slide where you showed the layout? So it appears that you require quite a massive memory to store the key. Can you maybe compare how much memory you need for the internal functions, SRAM, and how much just for the key? So is it dominated completely by the key, the memory requirements?
The memory requirements I show later only include the FIFO we use for double-sized syndrome computation, right?
Yeah.
So these results don't include the key memory. I don't know the exact ratio of the FIFO to the key memory, but we excluded them from the results intentionally to not skew the comparison between different designs.
And how would your design scale for the different parameter sets?
For the different parameter sets, I would say you would have to run some minor analysis to figure out an optimal folding factor, right? But I think it would still, our approach for computing error locator polynomials would still be advantageous also for the other parameter sets. But as I said, you would first have to run short analysis to figure out the optimal folding factor, because that significantly influences the achievable efficiency.
Thanks. So looks like there are no further questions from the audience. So let's thank the speaker again. Now we have the final talk of the day. It's an online talk. It's about, because I don't know how to properly pronounce the acronym, I just say it the long form, syndrome decoding in the head in hardware. The talk will be given by Sanjay Deshpande, and yeah, it's an online talk. So.
Hello, everyone. Thank you for attending my talk, which is titled SDITH in Hardware. It is a joint work along with my PhD advisor, Jakub, and our collaborators from Sandbox, James and Stephen. The main motivation behind this work is that we all know that quantum computing is this exciting new paradigm of computation that holds tremendous potential and could solve complex mathematical problems which are hard for existing high-performance computers. It has applications in various fields like life-saving pharmaceuticals, green battery technology, and so on. However, they pose a significant cybersecurity risk. Large-scale quantum computers can break existing public key cryptography standards, which rely on hard problems such as integer factorization. Hence, there is need for quantum-safe cryptography, and this is where post-quantum cryptography emerges as a beacon of hope. In order to standardize post-quantum cryptography algorithms, efforts are in progress all around the world. Organizations like NIST, ISO are leading the standardization effort. In the standardization process, the algorithm proposals that are being submitted mainly belong to two different categories. The first one is the key encapsulation mechanism scheme, and the second one is the digital signature scheme. And the evaluation of these PQC algorithms in this standardization effort can be broadly classified into three areas. Primarily, the security of the scheme, then the implementation efficiency and implementation security, both in hardware and software, and then the cost. By cost, I mean the signature size or the key size and so on. This work is focused on hardware implementation efficiency and implementation security aspect of the digital signature scheme called syndrome decoding in the head, or SDITH in short. So here is how the rest of the talk is structured. I will start with a brief introduction to the scheme, then talk about key aspects of the hardware design and the challenges we face, discuss comparison with the related work, then we'll conclude with some future directions that we are exploring. The SDITH scheme comes in two variants. One is the hypercube variant, and the second one is the threshold variant. And each variant could be realized in three different security levels: level 1, level 3, and level 5. And each variant can in turn be realized into two different arithmetic fields that are used in the syndrome decoding instance. And then, depending on the security level we are operating in, there is a parameter D for the number of splits that offers splitting big syndrome computation instance into two smaller instances. Like any digital signature scheme, SDITH also has three primitives: key generation, signature generation, and signature verification. And here is the algorithm for key generation. And below that is the scheduling that we use in our hardware design. And as we can see, key generation allows some algorithmic level parallelizability that we could take advantage of in our hardware design. Out of these, all the elements, the blocks which are highlighted in green are constant time, and the one that are highlighted in red are variable time due to the rejection sampling. However, the sampling is performed on the public element, so we could consider the overall design to be constant time. Now, coming to the signature generation process, there is only a little scope for parallelism when compared to key generation. But one thing that we observe is that the processing of the message happens much later in the algorithm. And hence, we could divide the signature generation algorithm into two phases, offline phase and online phase, where in the offline phase, we do all the pre-processing that is required once before the message arrives. And once the message arrives, then in the online phase, we do all the operations that use the message. So here is how the scheduling for the signature generation offline phase looks like. And as I said earlier, it's pretty sequential. And most of the operations in the offline phase use SHAKE-256, which is the PRNG that is used. And there is some possibility for parallelizability, but this comes at a cost of additional hardware. For example, the modules that are used inside the multi-party computation modules like compute plane broadcast. Similar to the offline phase, even in the online phase, the algorithm is pretty sequential, and the scope for parallelizability is possible at the module level, again, at the additional cost of hardware. And here it is the party computation module. Similar to sign offline and online parts, there is not so much scope for parallelism at the algorithmic level in the verification algorithm as well. However, there is a possibility of parallelism at functional level or the module level at cost of additional hardware, just like sign online and sign offline phases. In addition to that, there could be techniques like loop unrolling and so on that also requires duplicating the modules. But for this design, our target was to keep area as low as possible. So for that reason, we go with only one module for each operation. Now, moving on to our hardware design. Our hardware design uses pyramid-like structure for construction of all three modules together, in which at the lowermost level of the pyramid, we have both arithmetic field that we operate in different variants of SDITH, and also the shake module, which is used as a PRNG and as a hash function. Then one layer up, we have the pseudo-randomness generation, hash generation, and the syndrome computation and the syndrome decoding instance. And that share the modules that are available at the lower level. And on top of that, we have the multi-party computation modules, and which use the lower level modules. And finally, on top, we have the primitives, the key generation, signature generation, and verification modules. Our contributions from this work are: we design and implement first parameterizable hardware realization for hypercube variant of SDITH signature scheme. We propose two variants of syndrome decoding modules, which is sample first, then multiply, and sample and multiply on the fly. And we split the hardware implementation of sign into offline and online phases to optimize the overall time taken for signature generation. And we show drastic reduction in terms of clock cycles when compared to the optimized software reference implementation. And in key generation, the improvement is up to 250x. In signature generation, it's up to 3.4x, and in verification, it's 2.2x. Now let's start with looking into the details of the syndrome computation module that is used inside the key generation. In this case, we need to sample both the H matrix as well as S vector for the computation of the syndrome. So we start with sampling the random bits that are required for computation of S, and then we start computing the S value. And in parallel, then the shake is now assigned for computing the expand H. And once both the computations are done, finally we perform the matrix vector multiplication and addition. So since in this case, we need to sample first and then multiply, we use the sample first and then multiply approach. Now coming to the syndrome computation module that is used inside the sign and verify part. Here, the SA and Y values are already inputs to the module, and we only need to compute H. So in this case, rather than computing H, full H value, we just stream the H value directly from the PRNG into the multiplication unit that performs the syndrome computation. And this way, we sample and multiply on the fly. And comparing both the approaches, we see saving both area and time. Sample and in the sample and multiply on the fly approach. Additionally, since we don't store the H matrix completely, we also save significantly on the number of the amount of block RAMs that we use. A similar trend can be seen in terms of GF251 designs as well. When it comes to the time taken for the computation of the overall syndrome, between the comparison between the GF256 versus the GF251 designs, the GF251 designs are slower because there is an additional cycle cost for prime field reduction. And for performing dot products inside the matrix vector multiplication operation in GF251 design, we use DSPs that are available on the FPGA. The next important module used in the SDITH scheme is the evaluate module. It is used inside the MPC modules. The evaluate function takes as input an FQ vector representing the coefficient of a polynomial FQ of X and a point R and computes evaluation with this equation that is given below. And when we profile the SDITH algorithm, evaluate is used in both sign and verify operations, and it contributes to 99% of cycles of the online part of the signing and 70 to 90% of clock cycles in the verification based on which parameter set we are operating in. Among other operations, the most time-consuming one are the 32-bit modular exponentiations. In optimized software reference implementation, this is accomplished by two large lookup tables. Whereas for our hardware implementation, the target FPGA is a lightweight FPGA RTX7, and that does not have these resources to store all the possible values for 32-bit modular exponentiation. So we take an on-the-fly computation approach. To make the best out of the on-the-fly approach, we use the register stages that is inside that are available inside the modular multiplication unit and compute multiple modular exponentiations in a pipeline fashion to achieve some speed. The next module that I would like to talk about is the top-level module for the signature generation. The block shown here on the right is our area-optimized implementation. As mentioned earlier in this presentation, the signing operation is divided into two phases, offline and online, and they both run in parallel. Shake is used as a hash function and a PRNG in SDITH signing, and it is used in both offline and online phases. However, Shake 256 is area intensive. It uses around 31% of the overall hardware design area. So rather than having two individual Shake modules, one for offline phase and one for online phase, we only have one Shake module that we share between online and offline phases. And we accomplish this sharing using the Shake scheduler. The scheduler module ensures this switching without any clock cycle wastage. On the bottom right corner is a sample timing diagram that shows the working of our sign module. We first start with message 1 in the sign offline phase. And then once the computations are done, all the data that is required by the online part is now buffered into the memory buffers. And then the sign online part starts working on the data related to M1. While in parallel to that, sign offline now already starts working on the second message. And this way we are able to hide all the cycles taken by the offline part starting from the second message. Now coming to the comparison with the related work, the only related work that we could compare our work directly against is the optimized software implementation for SDITH. From the plots, we can see that in terms of key generation, there is significant amount of improvement in terms of overall clock cycles. And this is because key generation algorithm itself has some algorithmic level parallelism. And in terms of sign and verify, there is also improvement, but it is not as much as much we see in key generation. As mentioned earlier, the lower level prime field arithmetic that we use in GF251 design also has significant impact in terms of overall clock cycle count when compared with GF256. And this can be seen in both software as well as hardware implementations. In terms of key generation, the GF251 optimized software reference implementation is faster than the GF256 because they use Galois field new instructions from Intel for optimizing some of the lower level arithmetic. Out of all the clock cycles taken for both signature generation and verification, in terms of hardware, 70 to 99% of clock cycles are taken by the evaluate module. When it comes to the time comparison, things change. The keygen is still 11 to 17 times faster, but sign and verify are slower. Firstly, this is because the operating frequency of the lightweight FPGA RTX 7 is at 164 megahertz, whereas the Intel Xeon processor, which is used for the optimized reference implementation, is being operated at 2.6 gigahertz. And secondly, we compute the evaluate function on the fly as we are computing them, whereas in the optimized software reference implementation, this is stored in large lookup tables. Now, comparing it against the other signature candidate hardware implementations that were out in the literature when we published this work, in this plot, on the left, we have the latest NIST competition candidates, and on the right, we have the old NIST competition candidates. It is difficult to compare them directly since the construction of these algorithms is different, and also the target architecture for the hardware implementation can also be different. But the idea behind this plot is just to give a sense of where STITH stands in terms of comparison of both time and area with other candidates. And as we can see from the plot, SDITH could be realized with a small area footprint. However, one thing that stands out is the block RAM utilization. SDITH requires significant amount of storage. And in addition to that, since we go for this offline and online approach, this also requires some amount of buffering, which also adds up some amount of memory in the overall block RAM count. In conclusion, in this work, we present the first hardware realization of SDITH signature scheme that is parameterizable across 3 different security levels and 2 different arithmetic field. And as we saw in the result, SDITH could be realized as a low area design. However, the overall memory consumption is quite high. As part of the future work, what we have in plan is that the lower level modules could be reused, and the threshold variant of the SDITH could be implemented in a straightforward way. Module level parallelism could be exploited to construct high performance designs, especially by using multiple evaluate modules. And also the MPC hardware modules components that we implement could be reused beyond SDITH. With that, here are the references that I've used, and thank you for your attention.
Yeah, that's a bit difficult. So the only option, Sanjay is online in the Zoom room. So if anyone has a question with a possibly short answer that he can type it in, then please go ahead. If anyone else, or if you have a longer question, you might get into the Zoom room and ask him directly. I think that's more easier option than for me to just read out the answer. I don't think this will come properly across. So are there any questions? Okay, if not, then I say please contact Sanjay directly in Zoom if you have any questions. Let's thank him again anyway. And yeah, so that's it for this session and for the day.